So the second case of integrating rational fractions is when the factors of the denominator are all linear and some are repeated. So if the linear factor ax plus b is being repeated, so we are going to write these partial na fractions. So for example, okay, if this is the denominator, there is a common factor no, for the two terms. So we can factor it out. There's a dx supposedly. So this is equal to, just copy the numerator. Okay. So this is a proper no fraction because the degree of the numerator is less than the degree of the denominator. So x squared is a common factor. So factor it out. So what remains here is x plus 2, okay, which is a linear factor. So meaning this is a cubic expression. So we are going to have at least three, um, not at least, we need three partial fractions. Okay. So x here is a linear factor, although there's no constant term, but of course b can be 0, right? So we can just have x, okay, for a linear factor. So it's being repeated. So meaning we need two partial fractions for the x squared and another partial fraction for the x plus 2. So this would be equal to an a where we need to compute for its value. So we'll start with the first linear factor. So for this case, so we need another partial no fraction for the repeated um factor of the denominator. So if ever, for example, there is an x cube, so we need another partial fraction. Okay, let's say c over x cube, etc. And don't forget there is another linear factor, x plus 2. So it's only x that is being repeated. So we need another linear factor, another partial fraction for the other linear factor na x plus 2. So we need to solve for a, b, and c. So let's compute for a, b, and c here on the side. So same process with case 1. So just copy the fraction, put it on the left side of the equation. Then the partial fractions on the right side. So again, this corresponds to a over x plus b over x squared and c over x plus 2. So same process of multiply the entire equation by the denominator so that the left side now becomes na lang equal to the numerator. Okay. Wait. So the right side, we are going to multiply this first term with x squared and x plus 2. So the result would be x times x plus 2. Will no longer write everything. I hope you can just imagine, no? So multiplying the first term by, yes, I'll just write it na lang. So multiplying this first term with, okay, multiplying that with um, x squared and x plus 2. So what remains is x and x plus 2. And then for b, multiplying it with x squared and x plus 2. So what remains is x plus 2. And for c, if we multiply it with x squared and x plus 2, so what remains is x and x plus 2. or rather x squared, because it's already an x plus 2, so x squared and x plus 2, so cancel out the x squared, so what remains is x squared. So for the second term, it's going to be x plus 2, and for the third term, it's x squared. Okay. So in case number 1, the method that was used was assign values of x such that one, at least one of the terms would be equal to 0 so that you can solve for the constants. Okay. So another approach, another method is just to express everything as one polynomial. Okay. And then we'll be forming at least three, okay, equations later. So again, this is another method. So the first step is to express everything as single na polynomials. So if there are what they call this, if there are similar terms, so we need to combine them. Okay, so for the left side, sorry, so I'm gonna say everything on the left side and everything on the right side, by the way. Okay, so the right side, if we multiply x and x plus 2, it becomes x squared, no, plus 2x. Then for the second term, we have, okay, it's x plus 2 and c x squared. Okay. So if we're going to distribute the constants, although this step is not required, but let's show the complete, no, solution, multiplying second term, the b, with x plus 2, and then this is cx squared. So we combine similar terms. Okay, we start off with x squared. So we have two terms containing x squared. Okay, so this term here, okay, so this term ax squared and cx squared, so they both contain x squared, so they are similar terms, meaning we can add up a and c, okay, and then factor out the common, no, factor x squared. Then for the x terms, we have 2a plus b, right? And we have only one constant term, 2b. So let's write again the left side of the equation. So the right side now is expressed as a single, no, polynomial, also the left side. So there is an x squared term here, also an x squared term here, an x term here on the left side, also an x term here on the right side, constant term on the left side, and a constant term on the right side. Okay. So after expressing, okay, everything on the left side and the right side as single polynomials, okay, so we equate uh, what do you call this? Equate similar terms. Similar terms from each side of the equation. So starting off with the x squared term, so we have negative 2, no, x squared, meaning that is equal to a plus c. x squared, right? Or if we are going to remove the common factor x squared, so negative 2 therefore is equal to a plus c. So this is equation number 1. So we have two unknowns. So we need another equation containing a and c so that we can solve for the values of a and c. So let that be equation number 1. Okay. Now for the x terms, so we have 23x on the left side and 2a plus b times x on the right side. So meaning 23 no, is equal to 2a plus b. So we have another equation, this time containing a and b and not a and c. So there's another value that is introduced, another letter that is being introduced. So we need another equation because we have three unknowns, no, a, b, and c. So we need another equation so that we can solve for the values of a, b, and c. So we have the third term, which is the constant term. So if ever there is a missing term, you can equate it to 0. Okay, but for this one, there's a constant term on the right side. Now, just in case on the left side, for example, there's no constant term. So you can still make an equation, okay, wherein the left side is 0. But for this one, it's negative 9 equals 2b. So we have, okay, an equation for b. So since there's no other unknown here, then we can right away solve for b. Okay, so b therefore is equal to negative 9 over 2, right? Then for equation 2, okay, since we already have the value of b, so we can solve for a. Okay, and for equation 1, once we have the value of a, we can already solve for the value of c. So if ever the resulting system of equations, okay, have the unknowns, okay, wherein you cannot solve for just one unknown directly, unlike this one, no? So you, of course, know how to solve systems of linear equations by using substitution method or elimination method, or by what they call this, using a calculator, if you are allowed not to use a calculator. So let's have this manual no solution so that would be fair to everyone, okay, especially those with calculators that cannot solve for systems na of linear equations, and especially if the number of linear equations will be how many na, no, so more than 3 or more than 4, because in some calculators we can solve for systems of 4 linear equations. So I think the maximum number of equations is 4. Okay. So if ever the number of equations would be greater than 4, so of course you can no longer use no a calculator. So we need the different methods in solving systems of equations. So for this one, this is a simple one. Okay. So from equation 2, solve for a because we already have the value of b. Okay, so it's 23 equals 2a plus b. So just plug in the value of b. So that's negative, no, 9 halves. So for we multiply the entire equation by 2. So this becomes 46. And then this is 4a minus 9. Transposing 9. We have 55. No, equals 4a. So a, therefore, is equal to 55 over 4. And then for the value of c, we can use equation number 1, since we already have the value of a. So from equation 1, solve for c. So solving for c, so it's negative 2 equals a plus c. So negative 2 is equal to 55 over 4 plus c, or multiplying the whole equation by 4, it's negative 8 equals 55 plus c, or c is negative 8 minus 55, or that's negative 63. Okay, so c is negative 63. So therefore, the equation, or rather the expression, okay, a over x. So we have 55 over 4 over x. Or you can write it as 55 over 4 times 1 over x if you want to. Okay, plus b is the value of b. It's negative 9 halves. So it's negative 9 halves over x squared. And then plus c, negative 63. Okay, negative. Wait for a moment. It's not negative 63, sorry. Everything must be multiplied, no, by 4. So the last term must be 4c and not c. So it's not negative 63. It must be a fraction. Or, yeah, a fraction. So it's supposedly 4c. So 4c is equal to negative 63. So c is negative 63 over 4. And there is no common factor for 63 and 4. So negative 63 over 4. X plus 2. So we can now integrate once the partial fractions are formed. So we can already apply integration. Okay, so the first term, you have 54 over 4 ln of x, right? For the second term, okay, this can be written as negative 9 halves x raised from negative 2. Okay, applying power rule, it's negative 9 halves. And then this becomes, negative 2 becomes negative 1. If you add 1 to negative 2, no, it's negative 1. So that's x rep of negative 1 over negative 1, or it's basically times negative 1, no? X to the power of negative 1. And then minus 63 over 4, okay? Natural log of x plus 2. And then plus c. Or write the second term as plus 9 over 2x. You will transfer x to the denominator. So then negative 1 becomes positive 1. Okay, and then minus 63 over 4, natural log of x plus 2, then plus c. So this is the answer, no, for this one. Okay. So the integral of negative 2x squared plus 23x minus 9 all over x cubed plus 2x squared, okay, dx is this one. So that's for the denominator containing linear factors, and some of the linear factors are repeated.